to be talking about a subject in which I am a bit of a tourist, but there are some advantages. Sometimes tourists can see things that the locals can't. Suppose that you want to build a discrete model of space-time for whatever reason. The first thing you have to decide is what pieces of the continuum to keep. In causal set theory, the choice is to keep causal relations. That is, to give the information for any point of which other points are to its past and to its future. That leads to a diagram like the one on the slide, in which the dotted lines are not part of the set, but are indications of which points are to the past of other points. Now, such a structure is mathematically a partially ordered set where the mathematical statement that P precedes Q is translated as the physical statement that the event P is to the past of the event Q. It's a partially ordered set because points don't have to be related. If 2 points P and Q are in each other's present, then it's not true that P is to the past of Q or that Q is to the past of P. So this gives a mathematically well-defined and much-studied structure. It's called a partially ordered set. Causal set theory adds 2 more conditions to this. The first is a causality condition, that there are no points x and y such that x is in the past of y and y is in the past of x. In other words, no closed time-like curves, no time travel. The second is a discreteness condition. It just says that given any 2 points, x and y, there are only a finite number of points that lie between them. Now, that second condition is worth amplifying a little bit because it will be coming up later in the talk. As in the continuum, a basic ingredient in causal set theory is what physicists call a causal diamond. Mathematicians call an Alexandrov interval or an order interval, or sometimes just for short, an interval. The interval I of x, y is simply the set of points that are both to the future of x and the past of y. So in terms of light cones, it's the interior of the intersections of the light cones. Given that, the discreteness condition is just the statement that any causal diamond has only finitely many points in it. For future reference, I should say that in counting, it is usual to think of these as open intervals. That is, x and y, the endpoints, are not counted as members of the interval. There's no particular reason for that, but it's custom. Okay, there are lots of ways that you could try to set up a discrete model of space-time. What makes this one special? Well, the basic rationale is from some theorems of ordinary continuum space-time geometry that say that for a space-time that obeys a simple causality condition, the causal structure plus the local volume completely determine the topology and the geometry. A causal set is the minimal realization of this as a discrete structure. The causal order is built in, and the volume of a region is just the number of points in that region. Well, this makes for a nice rationale and nice slogans, but of course, the space-time that we observe appears to be continuous. So we have to ask how well a causal set can approximate what we actually see. This is really 2 questions in 2 different directions. In one direction, if you start out with a space-time you can ask, can we build a causal set that approximates this, and then use properties of the causal set to reconstruct properties of the space-time. In the other direction, if we start out with a causal set, can we find a space-time that it approximates? Now, in the first direction, we're in pretty good shape. There's a standard procedure for constructing causal sets out of a space-time, at least out of finite volume region of a space-time, called a Poisson sprinkling, which basically means that you just choose a bunch of points completely randomly, record their causal order, and then forget about the space-time. Such a sprinkling has a natural discreteness scale, roughly the typical distance between nearest neighbor points. And below that scale, not surprisingly, the causal set doesn't tell you much. But at scales that are large compared to the discreteness scale, we know how to reconstruct the dimension of the space-time, which is less trivial than it sounds, but then also the coarse-grained topology, the coarse-grained geometry, interesting geometrical objects like D'Alembertians and Green's functions. Now, I don't want to oversell this. There are still some really serious open questions. A lot of them revolve around how to quantitatively describe how close a causal set is to a given space-time, and also reconstructing ordinary space-time locality is tricky, although it can be done in the cases that it's been tried, at least that I know of. But all in all, we're in not bad shape, at least compared to the other direction, which is a complete disaster. Most causal sets look nothing whatsoever like manifolds. In particular, choose a random causal set. That is, just choose n points and randomly choose causal relations between them. If n is large, you are overwhelmingly likely to have something called a Kleitman-Rothschild order, or a KR order. A KR order is a particular kind of three-layer set, like the one in the top of the slide. That is, it's a set that can have arbitrarily large spatial extension, but only has 3 moments of time. That's not where we live. And when I say overwhelmingly likely, I mean that in a very strong sense. I mean that that when n is large, the set of causal sets that are not KR orders is of measure 0 in the space of all causal sets. Now that's a bizarre result, and you might hope that it's just a fluke, but it isn't. If you throw out the KR orders by hand, let's see if this, yes, that does go backwards, good. If you throw out the KR orders by hand, almost every remaining causal set is a 2-layer set, 2 moments of time. You throw those out, you get 4-layer sets, then 5-layer, 6-layer, long sequence of causal sets that look nothing like our space-time before you get anything that's even close. That sounds pretty bad, but let me give you a little bit of perspective on this. Suppose you're doing quantum mechanics just of an ordinary point particle, and you write down a path integral. If you look carefully at the path integral, you'll see that almost every path that appears in the path integral is not only not smooth, it's nowhere differentiable. We don't worry about that, or at least most of us don't worry about that, because we know that when you combine these in a path integral, the bad paths destructively interfere, and we're left with the good ones. So the question is whether something like that is true for causal sets. To answer that, you need to define a path integral. To define a path integral, you need some version of the Einstein-Hilbert action. That will take a brief detour back to this picture of causal diamonds or Alexandrov intervals. One of the characteristics of any interval is the number of points in it, which, remember, we're interpreting as the volume. A zero-element interval is just a link. It is 2 points that are causally related but don't have anything in between them. There's one way of making a one-element interval by sticking a point in the middle. There are 2 ways of making 2-element intervals. There are 8 ways of making 3-element intervals. The numbers of possibility goes up very rapidly. But given any interval, its volume or its size is a well-defined quantity. That means that given any causal set, we have a natural set of observables or invariants, which are simply the number of 0-element intervals, the number of 1-element intervals, the number of 2-element intervals, and so on. Now, in the continuum, the volume of a causal diamond depends on the curvature in a well-understood way. And so a few years ago, Diogenes, Benincasa, Faye Dowker, and then later extended by Lisa Glaser, showed that using that result, you can just take a certain linear combination of these numbers of intervals, and for a causal set that came from a sprinkling of a space-time, this gives you a very good approximation of the Einstein-Hilbert action, the integral of the scalar curvature. So we can just declare that this is the action more generally, and we can now write down a path integral, actually a path sum because everything is discrete, and ask whether somehow this suppresses these bad causal sets.
Is there some limit parameters there, or what? How can I see that it's Einstein-Hilbert?
So if you have a sprinkling of points on a given manifold, the density of the sprinkling is the control parameter. And you can simply work out on a given manifold with some known curvature what these numbers are, take the limit as the density goes to infinity, and you get the Einstein-Hilbert action.
Here, how can I see parameters? So the curvature comes and is the formula which you wrote.
Yeah, the numbers n0, n1, n2, and so on are numbers of causal diamonds with certain volumes. The volume of a causal diamond depends on the curvature of the space-time it's in. So the curvature is hidden there. It's a long calculation. I can give you a reference, but you write down those numbers on a manifold as functions of the curvature. You work out this combination. You take this limit, you get the Einstein-Hilbert action. It's a calculation.
I understand, but you assume already that there is curvature there, then you discretize.
Yes, so I'll get back to that at the end of the talk. This is definitely an action that comes from starting with a continuum that has curvature, figuring out how to discretize the action for that continuum in a way that applies to a causal set, and then assuming that that's valid for causal sets in general. That's an important difficulty. It's the last line of my paper, of my talk. I'll come back to that.
Did you say that this notion of approximation is approximate? Not really controlling, or in this case, you can control it?
In this case, one can control it. The corrections, when the sprinkling is reasonably dense, you get the Einstein-Hilbert action plus corrections that go as inverse powers of the density of the sprinkling.
So if I had higher order curvature terms, would I have then more ends?
Yes. Yes, there is an ambiguity here. There are a number of different expressions of this form that give the Einstein-Hilbert action at lowest order. The more complicated ones, some of them probably correspond to higher curvature. Some of them we just don't know what they mean. Okay, so we can write down this path sum, and we can ask questions about it, but that doesn't mean that we can answer those questions. The number of causal sets with n elements goes as 2 to the n squared over 4. So that's an enormous sum. But 5 years ago, a graduate student of mine, Sam Loomis, convinced me that it might be possible to actually evaluate this for the simplest possible causal sets, which are the 2-layer causal sets, the ones at the bottom of this picture. The basic reason that that's plausible is that if you look at the intervals, the causal diamonds here, there are only links. There are no intervals with more than 0 elements in them. Because an interval has to start at the bottom, end at the top. In order to put a point in the middle, you need a 3rd layer. So if you have only 2-layer sets, then the Benincasa-Dowker action, the N1, N2, N3 drop out. You just have an action proportional to the number of links. The first layer is the set of points with no points preceding them. The second layer is the set of points with no points preceding them when you eliminate the first layer, and so on. There are other more technical definitions of different kinds of layers, but that's the basic one. And it means, it really is counting the number of moments of time. It's looking at the maximum number of steps that you can take from the bottom to the top of the causal set. Okay, so the action becomes just the number of links. Furthermore, there's a maximum number of links, which you get just by putting half of your points at the top, half of your points at the bottom, and joining everything to everything. So you can describe the action just as a function of the linking fraction, the proportion of links that a given causal set as compared to the maximum number. Now, of course, there is a conservation of difficulty. Given that form of the action, you still have to count how many causal sets have a given value of p, a given linking fraction. But it turns out that there's some nice combinatorics, that you can find limits. You can find an upper limit for p, for the measure, the number of sets with a given p. You can find a lower limit in such a way that they squeeze together when the number of elements becomes large. And so to lowest order in n, you can actually write down the measure. So you write it down, you approximate the sum as an integral, you do a really, really careful steepest descent evaluation since everything is very small. And what you find is that the partition function for these 2-layer sets goes as 2 to the minus some constant times n squared, where for a large range of coupling constants, that constant c is positive. That's an enormous suppression. If you assume that the points in a causal set are say 1 Planck volume each, then a region of a cubic centimeter by 1 nanosecond has about n of about 10 to the 133. So that's 2 to the minus 10 to the 266. Those are gone. Okay, so that's a hopeful sign, but there are still all of the other bad causal sets, the ones that don't look like manifolds. As a next step, Sumati Surya and two of her students said, well, maybe this is too hard to look at, for instance, the KR orders, but let's simplify the problem by truncating the Benincasa-Dowker action, by hand removing the higher ends. Then you get the link action again, the same action as for the two-layer sets. The combinatorics is a little bit more complicated, but again, you can find a restriction that squeezes the measure in a way that lets you evaluate the path integral or the path sum. And you get the same suppression. Result number 3 by Peter Carlip, Sumati Surya, and myself is that truncation doesn't matter for the worst causal sets, the KR orders. That the terms that are dropped from the action are subleading in the number of elements in the causal set. That's a fairly complicated combinatorial argument, but the basic reason is very easy to understand. In the diagrams here on the left, I have a one-element interval. What makes it one element is that there is a single path from the bottom x to the top y that goes through the middle layer. On the right, I have a 6-element interval. That's a fat interval. It includes a whole bunch of points in the middle. The combinatorics just says that if you have a large causal set of this sort, the thin intervals are very rare because you have to exclude all of the other possible paths from the bottom to the top. And carrying that through in detail, I mean, one of the advantages of working with causal sets is that you can draw pictures and sort of at least understand what the combinatoric questions are, if not the answers. You work through the combinatorics, you find that this truncation of the action is harmless. Result number 4 is not actually a result yet, but I expect that probably within the next 6 months, we will have a proof that generalizes this to the whole class of non-manifold-like layered causal sets. Oh, I should say that result number 3, the preprint is completely written and should be out on the archive within the next week or two. So what's the conclusion? The conclusion is that the ordinary gravitational path integral, without having to add any extra details, very probably extremely strongly suppresses this huge class of bad, non-manifold-like, non-spacetime causal sets, while at the same time leaving the manifold-like ones alone, because the combinatoric arguments that I described only work for the layered sets, not for the random sprinklings. So that's at least a step towards saying that maybe starting with causal sets, you can reconstruct a space-time continuum. There are, of course, open questions. We don't know whether there are other bad causal sets that still dominate the path sum that we would have to get rid of. We don't know that because we don't really have a general complete characterization of causal sets. In fact, we don't even know how to determine, given a causal set, whether it's manifold-like or not. We can construct causal sets that are manifold-like, but if you just give me one, I can't look at it or apply some known algorithm and tell whether it came from a manifold or not. And then the final issue is exactly the one raised earlier, that the action here was derived by starting with the continuum, figuring out the Einstein-Hilbert action, and then assuming that that worked for causal sets. That's not necessarily wrong, but it's not what you would do if you really think causal sets are fundamental. What you ought to do is figure out some argument entirely within causal set theory that gives you that action. Now, for this particular suppression, it almost doesn't matter, because all you need is that there's a term in the action that counts the number of links. But for more general questions, if you want to recover general relativity, you'd better be able to get something like the Benincasa-Dowker action from first principles. And as far as I know, we're a very long way from doing that. So on that note, let me stop.
Thank you, Steve. Very stimulating talk. Do we have any questions? And we are running very late on time, so we're suggesting that we go, in a sense, straight into this. Well, first of all, questions for Steve, but then we'll merge into the general discussion, and we will have that until 5:15, so that's 20 minutes, because we were supposed to finish at 5, and it's 5 to 5 now. Okay, so Slava first.
Yeah. How you define the dimension of the space?
Okay.
Because as you know very well, okay, dimensions will define notion only for continuous manifolds.
Right. So that is tricky. There are a number of different definitions of dimension. The most commonly used one, again, uses causal diamonds. And if you can ask on a manifold of a given dimension, if you take a large causal diamond, how many smaller causal diamonds does it contain that are of some given size? And for a manifold, that result depends on the dimension, obviously. If you have higher dimension, you can pack in more small causal diamonds in a big one. And it depends on the dimension in a way that if you take certain ratios, everything else cancels out except the dimension.
The problem is the following, that you assume some kind of structure between the sets, okay, in your causal sets, between the points in your causal sets. It's like in logistic, perhaps, where you concentrate on curvature in the corners, but nevertheless there are still substructures there.
Yes, so there is as you say, there's a basic difficulty or ambiguity here, that dimension is well defined for a causal set that is obtained by taking a high enough density of random points on a manifold where the dimension is defined. So that is the dimension that I'm talking about. The only time that I talked about dimension was to say that if you have a causal set that's obtained from a manifold in that way, then you can reconstruct the dimension of the manifold from the causal set. In general, this procedure doesn't give you an integer even. For KR orders, it gives you a dimension of 2.3 or something like that. Dimension just isn't defined for non-manifold-like causal sets, or it's defined but not in any unique way.
Yes, Steve. So I don't want to be discouraging, but of course, you know, the essential problem is that there are just so many of these sets.
Yes.
So, and of course, it will be exactly a hierarchy. You know what the worst of the worst. Those you can easily count, right? So the KR ones. But of course, there will be a hierarchy that, you know, whose entropy grows not with Cn squared, but with some other constant n squared, and then there are lots of, you know, n log n, e to the, you know. So all of these you hope to cancel in some systematic way, then just leaving over nice things. I mean, what's the outlook here? What can give us hope, really?
I don't want to come into this terribly hopeful, but I wouldn't feel terribly hopeful about almost any approach to quantum gravity. The fact that there is this systematic classification now of layered causal sets by a mathematician named Prommel and collaborators who I don't remember. And for those, the structure of the space of causal sets is well understood. And there's this process of a phase transition from domination by one type to domination by another, and so on. I absolutely don't know whether, well, I do know that there are other bad ones, but they're bad. The ones that I know are bad ones that are already eliminated by this argument. You can take a KR or make a sandwich, a KR order, good sprinkling, a KR order on the top. You can do that in lots of different ways, but those still get killed because they have the KR orders in them. Other than that, I just don't know. I thought that it was interesting that this seemingly first impossible step turned out to be possible and analytically, not computationally. After that, one can hope.